Hi, welcome back to Educator.com. Today we're going to talk about vectors. So this starts off an entirely new section for us. We're getting into really new territory. We're going to talk about vectors, and then later on we'll be talking about matrices. But first, let's talk about vectors. When we talk about the force on an object, we need to know two things: the magnitude of the force, how hard it's being pushed, and the direction, which way it's being pushed. So if we're going to talk about something being pushed, we can't just talk about how hard it's being pushed. We also have to know which way it's being pushed, right? It's very different to push something this way than it is to push something this way. But even if we know the direction, we also have to know how hard it is, right? We're pushing really hard versus pushing very slightly. Big differences here. So we need to know both magnitude and direction. We need to know how hard and which way. Now, one number on its own won't be enough to get across both pieces of information. So this leads us to the idea of a vector, a way to be able to talk about magnitude and direction at the same time, to be able to talk about both of these things in one piece of information. Vectors are massively useful. They're used throughout math, they're in the sciences everywhere, especially in physics. They're in engineering, computer programming, business, medicine, and more fields. Pretty much if a field even vaguely uses math, it's going to use vectors. So this is a really useful thing that we're talking about in this lesson. Now, I want to point out this lesson will use some basic trigonometry to figure out angles, so make sure you've got some familiarity with how trigonometry works so that you can understand what's going on when we're figuring out angles. All right, let's go on. The idea of a vector. So a vector is just trying to get across the idea of length and direction. Graphically, if we look at a picture of it, it's exactly that. It is a directed line segment, a length with direction. So it's both of these things at once. So in this case, we're starting at 0, 0, and we've got this length here, and the arrow at the end says that we're going in this direction. So we've got a chunk of length, and we see which way it's pointed, right? It's pointed in a very specific direction. It's got some angle to it. How do we call out a vector if we want to talk about a vector? Normally we denote it with an overhead arrow like this. So U with an arrow above it says that we're talking about the vector U, or we can put it in boldface with, a bold U. And once in a while, if we're talking about vectors, like nothing but vectors and there's nothing else showing up, sometimes it will just be assumed, but we're pretty much never going to see that, not in this course. Vectors are normally shown with lowercase letters. However, just like variables, you can use any symbol, but for the most part, we'll stick with lowercase letters. U and V are very common letters for talking about them. One last thing, we use this U with the arrow on top, and that's how we'll be denoting it in this course, although you might see boldface in textbooks. When you're actually writing it by hand, I write it like this, where I sort of don't really have a full arrow. I have more of a harpoon where it's just an arrow on one side, just the sort of like arrow flange on one side. So that's how I write it. You could write it with an actual arrow on top, nothing wrong with that. But, I'm lazy like us all, and so I just tend to write it like that because it's the fastest way that I know of to write it, but it still gets across the idea of a vector. So this is a perfectly fine way to write it by hand when you're working it out, but when we've got it actually written out in this lesson, we'll have it like that with an arrow on top. We can also give the vector algebraically by its location in the plane, right? So we have got these nice rectangular coordinates, so we can break that into components. So we call this the component form. So we've got a horizontal amount of 3, a vertical amount of 4. So we say its horizontal component is 3 and its vertical component is 4. U, the vector U, equals 3, 4. The first component is the horizontal one, the second component is the vertical, just like when we're talking about points in the plane. We normally use angle brackets. See, these are angle brackets because they're at an angle, but to denote vectors, but we will often also see parentheses. Parentheses are very common as well. I personally actually tend to use parentheses more, but most precalculus math analysis courses, most of those courses tend to use angle brackets, so I'm teaching with angle brackets, but personally when I'm just doing math on my own, I often tend to use parentheses, but either of them is just fine. After we learn about unit vectors, we'll see one more way to talk about the component form using I and J, but we'll leave that until a little bit later once we've actually talked about unit vectors. If we know the component form of a vector, we can figure out its length by the Pythagorean theorem. Remember, the Pythagorean theorem says that the hypotenuse to a triangle is the hypotenuse squared is equal to both of the legs squared and then added together. So that means we can take the square root of both sides of this equation. We've got the hypotenuse is equal to the square root of each leg squared and added together, right? Square root of leg squared plus leg squared. In this case, we know that our vector is 3, 4. So we've got one leg is 3, one leg is 4, right? One leg is 3, one leg is 4. So we work this out. Square root of 3 squared plus 4 squared becomes square root of 9 plus 16, square root of 25, when we get 5. So we see that the length of this vector is 5. When we want to denote the magnitude of a vector, when we want to talk about the length of a vector, the magnitude of a vector, we normally use the word magnitude to talk about length, but in either case, length, magnitude, we're just talking about how long is the vector. We normally use these vertical bars on either side of it, just like we do with absolute value. And we'll talk about that in just a moment, why it is like absolute value. Also, sometimes you'll see it written as double bars U, double bars on either side. So vector U with double bars around it. In either case, whether it's single bar or single bar, what we're talking about is how long is that vector, if we measured from the origin out to its tip. So if U is equal to A comma B, then the length of U, bars on either side of U, which would also be bars on either side of A comma B, because that's just a vector as well, will give us the square root of A squared plus B squared based on this exact same reasoning that the hypotenuse, the length of our hypotenuse, is equal to the square root of each leg squared and added together. So in this case, A and B are just there and there on our vector. Now, I'd like to point out real quickly, why in the world are we using vertical bars on either side, just like we did with talking about absolute value? So let's think about that for a bit. Let's think about when we work with absolute value, say we've got 0 here, and here's positive 5, and here's negative 5. Well, if we talk about the absolute value of 5, and we talk about the absolute value of negative 5, in both cases, we're going to get the number 5 out of it, right? We get 5 in either case because what the absolute value is telling us is it's saying how far are you from 0? How far are you from the origin? So the reason why the absolute value of 5 is because it takes 5 units of length to get from 0 to 5. And that's the exact same reason why the absolute value of negative 5 is because it takes 5 units of length to get from 0 to negative 5. They go in different directions, but it's a question of how far away is it. They're both 5 units away from the origin. The same thing is going on when we're dealing with a vector. When we talk about the size of a vector, what is the length of a vector, we're asking how far is the vector go out from the origin. So in both the case of the absolute value and the magnitude of a vector, what we're saying is how far are you from the origin? So we put bars around the U because it's basically doing the same thing as bars around a number with absolute value. Bars around a number is saying how far are you from 0. Bars around a vector is saying how far are you from the origin. So it's both a question of length effectively. All right, direction and angle. If we know the component form of a vector, we can figure out its angle through trigonometry. So once again, we've got U equals 3, 4. So tan theta equals side opposite over side adjacent when we've got a right triangle. And we've got that here because we know we're dealing with a nice rectangular coordinate system. So we've got 3 here and 4 here. So our side opposite to our angle theta is this side here, and our side adjacent is this side here. So that gets us tan theta equals 4 over 3. So at this point, we can take the arctan of both sides, the inverse tangent. Arctan and tan inverse mean the same thing. I like arctan. So theta equals arctan, tan inverse of 4 over 3. We plug that into a calculator or look it up, and we see that that's approximately equal to 53.13 degrees. So we see that that is the angle in there. Now, we normally talk about direction as the counterclockwise angle from the positive x-axis. It's a little bit confusing, but it just means we start over here at the positive x-axis, and then we just keep turning counterclockwise until we get to whatever thing we're trying to measure out to, at which point we stop, and that's the measure of the angle that we're going with. It's just like we did with the unit circle, right? We started at x-axis positive, and then we just kept spinning until we got to whatever angle we were trying to get to. But sometimes we won't be using the positive x-axis. So that's what we normally wind up using. But sometimes the reference location, sometimes, will change. And we won't be using this nice positive x-axis that we're used to using, but maybe we'll be talking about how far are we off of the, vertical y-axis to the right. Or maybe some other thing like we've got this other angle here created, and we're talking about how far are we off of this other thing in some angle going clockwise. So who knows how it's going to be done. We have to pay attention to what the specific problem is, how it's set up. It generally will be the positive x-axis. but it's not an absolute guarantee. You have to pay attention. This means in any case, whatever you're dealing with, I recommend always draw a picture, because that's going to give you a way to be able to see what's going on. So draw a picture before you try to figure out or use angles. It will help you get a sense of what's going on and really help clarify things. All right. Now, what if we've got the component form? What if we talked about previously from taking the magnitude and angle and getting component forms. Sorry, we talked about the exact opposite of that. So now we're going to say, what if we know the magnitude and angle and we want to get the component form? So if we're trying to find what's the component form from magnitude and angle. So we can figure that out. First thing first, always draw a sketch. It'll help keep things clear and help you understand what's going on. And then from there, you just use trigonometry. So in this case, we've got a length of 6, right? The length of our vector u is 6. Our angle theta is 120 degrees. So we remember from trigonometry, cosine of 120, cosine of this angle here, is going to be equal to the horizontal amount of change, the x horizontal amount of change up until it drops down on its crossover, divided by the length of the segment we're dealing with. So cosine 120 equals x over 6. Multiply both sides by 6. 6 times cosine 120. Cosine of 120 is the same thing as negative 1/2. So 6 times negative 1/2 gets us negative 3. So negative 3 is our value for x. Similar thing going on for our y. Y, the vertical component, sine of 120, sine of the angle we're dealing with, is equal to the vertical component divided by the length of the entire segment, 6 in this case. So sine 120 equals y over 6. Multiply both sides by 6. Sine of 120 is root 3 over 2, so it simplifies to 3 times root 3 equals y. So at that point, we just take both of these pieces of information, we slot them into our u, and we've now got component form. Our u is equal to negative 3 comma 3 root 3. Now, I did tell us to do it with cosine 120, but most of us are probably used to dealing with trigonometry for numbers, for degree angles under 90 degrees, right? It's a little bit confusing, maybe just a bit, to be able to working with things over 90 degrees. So we also could have converted this to an angle of 120, so a total of 60 degrees over here, right? Because it's 180 on the whole thing. So we could have figured out that inside of the triangle is 60 degrees. Now, that's going to cause a little bit of difference here, because cosine 120 brought that negative to the table, because indeed our x is going to the left. And remember, this is the negative direction for x, right? Going this way gets us negative x values when we go to the left, just like going down gets us negative y values. So if that's the case, if we've got cosine 60, well, we can figure out, right, if you've got things inside of the triangle, you're just going to figure out the length of each of those sides. So cosine of 60 equals x over 6. So we'll get 6 times cosine 60 is just 1/2. So we get that 3 equals x. But notice what we're figuring out is we're figuring out here to here as x, which is not the same thing as the x value as in the horizontal location. What we're figuring out is we're just figuring out the length of the side. We're figuring out how far is it from here to here. But we have to figure out the horizontal coordinates, not just the length, but the actual x value. So if that's the case, what we're really figuring out is the absolute value of x. How long is our x? And that means that at the end, we have to look at this picture, and that's why we draw these sketches that are so handy. As we look at the picture and we see, okay, our x has a length of 3. However, it's going to the left. So that means it's got to be a negative thing. So by paying attention, we see that it is negative 3. Not just length 3, but negative 3. But it's because we drew a sketch that we're able to see this. So you've got this option. You can either just use the angle and be able to be really good at trig, or you can make it in a slightly simpler form where it's easier to understand, but you have to be paying attention and realize I have to set the sign at the end. I have to pay attention based on this sketch. Is this length going to come out to be positive? Is this length going to come out to be negative? You really have to pay attention to that. All right, ready to move on to a new idea. Scaling by scalars. If we have a vector u, we can scale it to a different length by multiplying by a scalar, a real number. So a scalar is just some number. It's not a vector, it's just an actual real number. Algebraically, the scalar just winds up multiplying each component. So let's say we start off with this red vector on our picture, which is u equals 3 comma negative 2. So we can scale this by some other thing by just multiplying it by some number. Like, for example, we could multiply u by 2. So we've got 2, and now that's the blue vector that we see there. Now notice that the blue vector is double the length of the red vector because it's 2 times u. So it just takes that length and it scales it by a factor of 2. It doubles that original length. Algebraically, we just wind up having this 2 multiply on the 3 and multiply on the negative 2, so we get 6, negative 4 as the components. We can take this, we can try multiplying by something else. How about a negative number? What would a negative get us? A negative winds up going in the opposite direction. So if we've got a negative u, then positive direction is the way it normally goes. Negative will be the opposite way, so negative goes in the opposite direction. So now we're going opposite the direction that u went, as we can see pictorially here. And for how it's going to wind up having, it's just a negative now on each of the components. So negative cancels out there, and we have negative 3, positive 2. And that's what we see on our picture. We could also have something that's not just a whole integer number, like, say, negative 3 over 2. So negative 3 over 2, we wind up being 3 over 2 times the length, right? 1.5 the length of the original vector, but then also in the negative direction, so opposite the direction of the first one. Once again, numerically, it just winds up being negative 3 over 2 times the first number times the second number, so we get negative 9 over 2, 3. That's what it winds up being. So algebraically, it just multiplies each component. Graphically, it's a question of stretching and maybe also flipping. In general, for a scalar k, any scalar k, and some vector u that is a, b, k times u, that's the same thing as k times a, b, so that's the same thing as just that k getting distributed to both the a and the b, so it gives us ka, kb. Great. A unit vector is a vector with a length of 1. So unit vector just means length 1. It still has a direction. It can have any direction, but it has to have a magnitude of exactly 1. So its magnitude, its length, how long it is 1 in terms of length. We create a unit vector out of any vector u by dividing u by its length. Remember, if we divide by a number, that's the same thing as just using a scalar. We're multiplying by 1 over the number we're dividing by. So previously, we could scale. So if we know its length is 10, and then we divide it by 10, we're going to get something that's length is 1 now. So we've got unit vector that is, we've got a vector u, right? Some vector u that is some length, but then we divide it by that length because the magnitude of u is just its length. So we've got that, we divide by that, we've scaled it back to what it would be if it was just at a length of 1. So our unit vector is the original vector divided by the length of the vector. This is the same direction as u, so it will be in the same direction, but it's going to have a length 1. It'll just be length 1. Now, the use of having a unit vector, the reason why it's so great to have a unit vector is we can just take it later and multiply it by any scalar k that we want, and we'll know that we'll have created a vector that is length k, because we started at length 1, you scale that by k, and we're going to go 1 times k, so we'll just be at vector length k, and we're going to be scaling in the direction we already started with, so we'll know we'll be in the unit vector's direction. This gives us an ability to easily create vectors of any length we want in a known direction. And this ability comes in really, really handy in a lot of situations, and that's why unit vectors are important. All right, we combine vectors. We can combine 2 or more vectors through addition or subtraction. It's actually not that difficult. We just add them component-wise. The horizontal components add together and the vertical components add together. All of your first components, they go together. Second components, they go together, so on and so forth, like that. So in this case, if we add 3, 4 and 2, negative 5, then what we wind up doing is we have the 3 and the 2, they get combined, and they become 3 plus 2, because we're adding 3, 4 plus 2, negative 5. Same basic thing, the 4 and the negative 5, they get combined, and so 4 plus negative 5 is 4 minus 5. We simplify that and we get 5, negative 1. We're just taking the numbers at the beginning, adding them together, the numbers at the end, adding them together. We're doing it component-wise. Each component stays and only mixes with components that are the same type. First components with first components, second components with second components, so on. So in general, for some u, u1, u2, so really that's just saying the first component of u, the second component of u, and then v1, v2, the first component of v, the second component of v. If we add u and v, u plus v, u1, u2 plus v1, v2 is going to be exact same thing, the u1 and the v1, the first components adding together, and then the second components, u2 and v2, adding together as well. Very similar thing if we wind up subtracting u minus v, well then it's just going to be u1, first component of u, minus the first component of v, v1, u2 minus v2, second component of u minus the second component of v. The components stay in their locations, but they either do addition or subtraction, depending on whether or not it's addition or it's subtraction. Makes sense. We can also do this geometrically and get an understanding of what's going on, because vectors are supposed to represent this thing, right? This directed line segment. So we can see this idea geometrically. You add vectors by placing the tail of one at the head of the other. So, for example, in this one, we've got u in red, 3, 4, and then we've got v in blue, 2, -5. So we put 3, 4 out to here. Right? That goes out to 3, 4, and then this one goes over 2, right, and goes down 5. So 2, -5, 2 to the right, down by 5. So we put those together and we get 5, -1, which is exactly what we see here in our in the purple vector that is the combination of them. So u plus v is the purple vector that we see there. So we can see this algebraically and geometrically, and the two ideas match up completely. Not only that, but we get the same resultant vector. This resultant, what we get when we put the two things together, is the same whether it's u plus v or v plus u, right? It doesn't matter if we wind up doing the blue one first and then the red one, right? We can add them geometrically in any order we please, and it still comes out to be the same thing, right? So we wind up seeing this parallelogram. We can see this as another way of adding things, as creating this parallelogram out of them, or just head to tail, but we see it geometrically what's going on. All right, now that we've got these two ideas, we can put together the idea of combining vectors with the idea of unit vectors to get a new way to express a vector's components. We start by creating two standard unit vectors, which is really just a fancy way of saying things that sort of make sense and are kind of fundamental. One horizontal, one vertical. So I, bold I, equals 1, 0. So it is a unit vector that is purely horizontal, and j, which is 0, 1, a unit vector that is purely vertical, right? This one is just, right, 1 unit long that way, and this one is just 1 unit long that way, purely vertical. And that's what we're seeing there. One other thing, if we want to write this bold thing, we can't really write bold on our paper. That's very difficult. You can wind up writing like an I, but instead of putting a dot on it, you put that little arrow on top, or in my case, the harpoon on top. Same thing with the J. You can make the J and then put a little arrow on top. And so that's another way of talking about these unit vectors, I and J, if you want to. All right. With this, we can express any vector in terms of I and j, right? If we've got 3, 4, well, that's the same thing as having 3 i's, 3 of these unit vectors that are horizontal, plus 4 of these unit vectors that are vertical, right? So that's what we've got there. We can combine them. We can break them up into 3 horizontal motions plus 4 vertical motions, and we get to the same thing as if we just done 3, 4 all in one go. So 3, our first component matches up with the i's, because that is just our thing of saying our horizontal, since our first component is our horizontal. And then our 4 matches up with the 4j, because that's just the same thing as saying 4 vertical or 4 units worth of vertical. And this also works for numbers that aren't just whole integers as well, because 4.7 times I just scales I by a factor of 4.7, so it will be in the same place vertically, sorry, not vertically, horizontally. And pi, we can also scale by a factor pi. As long as it's a real number, we can scale by it, so pi j there. Great. All right. We can also talk about a 0 vector. We denote the 0 vector with that same arrow top on top of a 0 that has 0 in all of its components. So it'll be nothing but zeros as the vector. It has no length, right? It's 0. It just lives at the origin. And so since it has no length, its direction doesn't matter. So here's an example, 0, 0, 0 vector, 0, 0, right? It's just sitting at the origin. Its distance from the origin is nothing because it's currently at the origin. Notice, for any vector u whatsoever, if we add u and the 0 vector together, we'll just wind up being there. We won't have moved anywhere because head to tail, we wind up going someplace and then we don't move because the 0 vector doesn't move at all. U minus u, if we subtract u from itself, well, we'll wind up going out and then coming right back, so we'll wind up getting 0. And then finally, if we take any vector and multiply it by a scalar of 0, well, we'll have some length, and then we bring that length to 0. So at a length of 0, we have the 0 vector. Great. All right, so at this point, we've talked about a lot of different ideas with vectors, and we can turn this into a bunch of properties. Don't worry too much about understanding all of these properties right off the bat. They'll sort of just make more sense, and you'll be used to using them. The beauty of all these properties is that they're very much what we're already used to using with the real numbers. So vectors, as long as you remember to keep it in this form of components only interacting with other components, they're very similar to working with numbers in many of the ways we're already used to. Let's talk through some of these properties. U plus v is the same thing as v plus u. This is the idea of commutativity. associativity, that 5 plus 8 is the same thing as 8 plus 5. We're used to that with the real numbers. We've also got associativity. U plus V plus W is the same thing as U plus V plus W, right? 3 plus 5 plus 4 is the same thing if you add the 3 and the 5 first, or if you add the 5 and the 4 first, right? 3 plus 5, then add 4, or 3 plus 5 plus 4. You add the 3 second. Doesn't matter which way you do it. So once again, very similar to doing it with normal numbers. K times L, if we've got two scalars, K and L times U, well, that's the same thing as K times an already scaled LU. So we can either multiply our scalars together, then multiply the vector, or we can have them multiply the vector each one after another. Same thing either way, which is pretty much what we'd expect. K times U plus V, hey, that's nice. It distributes. K times vector U plus vector V is K times vector U plus K times vector V. It also distributes in the other way. K plus L times vector U, the vector can distribute out onto them, so we've got K times vector U plus L times vector U. Great. If we take U and we add it to the 0 vector, we wind up just getting U. It has no effect. U minus U is going to get us back to the 0 vector. And then a couple more ones. 0 times U is going to give us the 0 vector. 1 times U has no effect. We're scaling by just what we're already at. And then negative 1 times U is going to flip us to the negative version. It'll just cause everything in there to become negative. The only one that might be a little bit confusing is KU is the magnitude of a scaled U, K scaled on U, K scalar times vector U. The magnitude of that is equal to the absolute value of K times the magnitude of U. Let's look at why that's the case. So real quick, simple example. Let's consider if we had 0, 1, right? So we've got this vector here that goes from here out to a length of 1. Right? So we could scale it by K, and let's say K is equal to negative 2. So we scale this. So here is our U, right? U equals 0, 1. So we could scale it by K equals negative 2. So negative 2 times U will get us same thing, but now it's going to be flipped, and it will be twice the length. Right? We're going to go down 2 units now. So whereas the first U went up by 1 unit, it had a length of 1. This has a length of 2, right? The fact that we're going down doesn't make it negative length. Length always is positive. So it's got a length of 2, which is why we've got this, the magnitude of 0, negative 2, well, that winds up being equal to positive 2, as we can see from this diagram right here. But if we'd separated this out into negative 2 times U, right? If we'd separated this out into negative 2 times 0, positive 1, what U started off as, well, we could break this by this rule into the absolute value of our scalar times the length of our initial thing, which would give us positive 2 times 1, same thing. So what it's doing is it's saying that the reason why we've got absolute value on the scalar here is because it doesn't matter that we're flipping and pointing in a new direction. Ultimately, length is always going to come out to be positive, so we can't let a negative K cause our result to come out as a negative length, because that just doesn't make sense, right? So we've got to figure out a way for it to always stay positive, and that's why we've got this absolute value here. All right. There's no multiplication between vectors. Even with everything we've seen so far about vectors, there's been no mention of vector multiplication, other than scalars multiplying on vectors. But other than that, we haven't talked about vector multiplication. That's because there's no good way to define vector multiplication. There's just no way to really do it that's going to make sense. So we could make up some numerical way to multiply vectors. So some vector times some vector makes some other vector. But it would probably be geometrically meaningless. We can't really come up with a good way that's going to have some deep geometric meaning. And that's the problem here. While we could come up with something numerically, we want all this stuff to have a geometric connection. All of this other stuff has. It makes sense to combine vectors, right? We're doing one vector and then we're doing another vector. We're doing 2 pieces of motion. Or stretch them. We have some piece of motion and then we just elongate it or shrink it or flip it. So those things make sense geometrically, but what would it mean geometrically? What would it mean as a picture to multiply a line segment by another line segment? It just doesn't really make sense. And because of that, we do not define vector multiplication. There's just no vector multiplication pretty much to talk of. Now, all that said, there is an operation similar to multiplication that's called the dot product. That's different though, because it will take two vectors, multiply them together, although it won't multiply them together. It'll take two vectors, and this vector dot this other vector will give us a scalar. It will give us a single real number. So don't worry about that too much now. We're not going to talk about it in this lesson, but we will explore it in the next lesson. So we will see it soon. But for right now, there's just no way to multiply vectors. And even later on, once you see something that's kind of close to it, you'll still see that it's very different from actually multiplying vectors and getting a new vector out of it. All right. Motion in a medium. A really common use of vectors is to analyze motion. The location of an object, the velocity of an object, the acceleration of an object. However, what happens if something is moving relative to a medium, like water or air? Like say we've got a boat in a river, and so the boat is moving up the river, but at the same time the water in the river is moving another direction. We have to do something to take account for this. So the object is moving in relative to the medium, but the medium itself is also moving, like the boat in the water. So to understand this, let's consider a fish swimming in an aquarium. I love this as an example. So first, we've got the fish. The aquarium is completely still. So we've got some table like this. And imagine that my arm here is the aquarium. And so here's the table. So the fish is here, and the fish is swimming forward, and the fish swims forward, and it gets to the other end of the aquarium. That's how it starts off in this picture here. The fish is the only thing moving. But what happens if we don't just let the fish be the only thing moving? If we take the aquarium and we grab the aquarium and we actually slide it to the side as the fish is swimming. If we grab the aquarium and we move it, so then we're going to see the aquarium move like this while the fish is moving like this. Because the fish is moving inside of the aquarium, but now the entire aquarium is also moving. So we see that the fish moves, but at the same time, the aquarium moves over. So it's very different from the world where the fish ended over here. Now the fish manages to move, but at the same time the aquarium is moved. So we have to take both of these things into account. We can see this picture pictorially here. So our fish is moving to the side, but at the same time the box is moving to the side as well. So the fish manages to get over to the left, but the box is now way over to the right. So if we're going to talk about where the fish has gotten to, the velocity of the fish, anything that we want to talk about the fish's motion, we want to analyze the motion of the fish, we have to take both of these things into account. We have to take into account the aquarium's motion, but also the fish moving inside of the aquarium. It's not enough to talk about just one of them. We have to combine these two ideas. So motion in a medium is the combination of the object's motion vector relative to the medium, right? The fish relative to being inside of an aquarium, and then the medium's motion vector. How is the aquarium moving? So how does the fish move in the aquarium? How does the aquarium move in a larger world? That's what we mean by relative to the medium. It's just whatever the thing is inside of, and then how is the thing that you were inside of moving? So we can break this down into the velocity of the object plus the velocity of the medium is equal to the velocity of the total motion. So the fish relative to the table is the addition of the velocity of the fish in the water plus the velocity of the aquarium as vectors, because the velocity vector in one case is going to be positive, in the other, for one of them it will be positive, for the other one it will be negative, because they're going to be pointing in opposite directions. All right. We can also talk about more than two dimensions. At this point, we've only seen vectors in two dimensions, but we can expand this idea to any number of dimensions we want. For example, a three-dimensional vector could be 5, -2, 3. No problem, we just keep putting in more components. By the way we define scalars and vector combination, everything we've discussed so far about vectors still works just fine. They might get a little confusing to picture in our head in higher dimension, but everything still makes sense. It's hard to picture higher than 3 dimensions because we're used to living in a 3-dimensional world, but it still makes sense in terms of the algebra of what's going on, and that's great. Also, one little thing, if we're talking about 3 dimensions, you remember that I, J, we could talk about unit vectors as an alternate way of talking about component form. There's another standard unit vector. There's K, which is 0, 0, 1. So I is the first component, J is the second component, K is the third component. So with this, we can express 3-dimensional vectors with I, J, K. So 5, -2, 3 would become 5i minus 2j plus 3k, right? 5 becomes 5i, -2 becomes -2j, 3 becomes 3k. Great, so we can combine them in terms of standard unit vectors as well. We can also talk about the magnitude of something that's higher than 2 dimensions. It might seem a little surprising at first, but it turns out it's actually really easy to figure out the magnitude, the length of a vector in any dimension. Consider the n-dimensional vector x, where x vector, vector x, where it is x1, the first component of x, comma x2, the second component of x, all the way up until we get to xn, the nth component of x. Now it turns out the magnitude of our vector x is just the square root of the sums of each of its components squared. Now, that seems a little bit confusing, but it makes sense. The length of our vector x is equal to the square root of the first component squared plus the second component squared plus all the way up until the nth component, our last component squared. So that seems really surprising the very first time we see this. We'll actually explore why this is the case, and it will make sense why this has to always be the case if we expand the idea that we'll see in example 3 to higher dimensions. Just think, oh yeah, that would just keep stair-stepping up, and that's why we see the square root of all of the components squared and added together. But you can also just memorize this formula if you want to, and it will be just fine too and work out. All right, let's see some examples. First, given that u equals 1, 3, v equals 4, 2, w equals -5, 1, what are each of the following? So 1, 3, if we're talking about u plus v, then that's the same thing as talking about 1, 3 plus 4, 2. So remember, we add the components together, so it'll be 1 plus 4 because they're both of the first components, and then 3 plus 2 because they're both of the second components. 1 plus 4 gets us 5, 3 plus 2 gets us 5 also, just by chance. So our answer here is 5, 5. Next, if we've got 6u, well, 6 times our vector is 1, 3. So the 6 distributes effectively. It's not quite distribution, it's a little bit different, but it has the exact same effect and feel. So the 6 multiplies each of the components. So we have 6, 6 times 3, 18. So 6, 18 out of that. All right, so we can probably start doing these scalars in our head. They're not too crazy hard to do. 1/2 times v, well, v was 4, 2. So 1/2 times 4, 2 is going to produce 2. 1/2 of 4 is 2, and 1/2 of 2 is 1. So we've got 2, 1 for 1/2 v, and then minus our w was -5, 1. We can distribute this negative here, so this becomes positive, this will become positive, this will become negative, right? We distribute that negative into there. And so 2 plus 5 is 7, 1 minus 1 is 0. There we go. And the last one, if we've got 2u minus 3v plus w, all right, so 2 times u, 2 times 1, 3 will become 2, 6. Minus 3 times 4, 2 will become 12, 6. Plus w was -5, 1. Great, so 2, 6 minus, so that would make that -12 plus -12, -6 plus -5, 1. At this point, we could add them all together. We could add them one by one, so it doesn't really matter how we approach this. Let's just add them the first two. So 2 and -12 becomes -10. 6 and -6 becomes 0. Plus, bring down the rest of it, -5, 1. So -5, 1 plus -10, 0. -10 and -5 becomes -15. 0 and 1 becomes +1. And there it is. So basics of vector addition and multiplication by scalars. It's very similar to what we're used to doing with numbers normally. It's just everybody stays inside of their slot. They only interact with other people from the same slot as them. First slots interact, second slots interact, and if it's higher than 2 dimensions, third, fourth, fifth, whatever slots interact. All right, next example, if u equals 4, v equals 6, and the two vectors make angles of theta u equals 30 degrees, theta v equals 120 degrees with the positive x-axis, what is the component form of u plus v, its length, its angle? All right, so let's do u in red. So over here, we first draw a sketch to be able to figure this out. So notice, if we're going to figure out u plus v, if we're going to get the component form of u plus v, well, it's hard to add angles and lengths together, right? We could draw, well, u is an angle of 30 degrees, so we'll go out like this. And then v is 6 at 120 degrees, so we'll be a little bit longer, 120 degrees, like that. And so our final thing will wind up being this, and we could measure what is that, but we'd have to have really, really precise stuff. We'd have to have like a really accurate ruler and be doing this with a protractor that was really good and be really, really careful to get all this. So it's not the sort of thing where we can draw it out and get a very good answer. So our first step is to get a component form out of each of them, because once we have a component form for u, a component form for v, it's easy to add them together. Then we add them together, and then we can figure out the length and the angle. So our first step is to get a component form. So u equals 4, our theta u is 30 degrees. Remember, it was with the positive x-axis. So our angle, 30 degrees, like this, So if we want to break down u into its x component and its y component, well then we know that cosine of 30, remember it's horizontal, its hypotenuse was 4, so cosine 30 is going to be equal to the x component of u, the first component of u, right, here is ux, the side adjacent, cosine 30 equals side adjacent ux over the hypotenuse 4, so 4 times cosine 30 equals ux. Cosine 30 is just the same thing as root 3 over 2, so we've got 4 times root 3 over 2, so we've got 2 root 3 equals ux. Very similar thing going on if we want to figure out what uy is. It will be sine of 30 equals uy over 4. Multiplied by 4 on both sides, 4 sine 30 equals uy. 4 times sine 30 is just 1/2, so 4 times 1/2. So we've got 2 equals uy. So at this point, we've got that u equals 2 root 3, its x component, 2 root 3, comma, and its y component, 2. And that's what our values for u are. Now, I want to point something out before we keep moving. Notice, right here, we were starting at sine 30 equals uy over 4, but we always get to this 4 times sine 30. So if you know the length, of your vector, and you know what angle it's at, you can actually just hop to length of thing times cosine or sine, if it's side adjacent or side opposite, respectively, of the angle, and that will just give you what that side adjacent or side opposite is, respectively. So we'll wind up doing that on the next one. If it was a little bit confusing, notice the parallel to how we just did it with the u vector while we're working on the v vector. But it's a really great way of being able to do this really quickly. Not really quickly, but it does help speed things up, and it's a good trick because you wind up seeing this an awful lot. So we've got 120 degrees here, right? We're at 120 degrees. Now, I think it's going to be a little bit easier to figure out in terms of this angle here, because it's easy to work under 90 degrees. So that is 60 degrees, right? 60 degrees, because 120 plus 60 equals 180. So now we want to figure out the Vx component, the horizontal component, and the Vy, the vertical component. So Vx is going to be equal to sine, so it's 60, right? So we've got 60 in the angle, and it's going to be side adjacent, so it's going to be the length, 6 times cosine, side adjacent, of the angle involved. However, there's one thing we need to notice. What we're figuring out here is we're figuring out the length of that side of a triangle, because the angle is inside of the triangle. So it's up to us to pay attention. Is it going to be positive? Is it going to be negative? Normally, we have the x direction go negative as we go to the left, right? That's negative x going this way. So that means we have to have a negative sign on our x component for v. Otherwise, it won't make sense, because we can see from the picture that it's going negative on the horizontal. So we have to pay attention to this. We have to notice this stuff happen, because otherwise it'll be a mistake. Okay, negative 6 times cosine 60. So cosine 60 is 1/2. So we get negative 3, Vx equals negative 3, Vy equals 6. This one's positive because it's going up. Sine of 60 is root 3 over 2. So that gets us 3 root 3. So we've got the x component is negative 3, the y component is 3 root 3. So our v vector equals negative 3, 3 root 3. Now, if we want to add these two together, so u plus v is simply a matter of adding them together. Our u was 2 root 3, 2. Our v was negative 3, 3 root 3. We add them together. We've got 2 root 3 minus 3, 2 plus 3 root 3. And if we want to, we could get what that is approximately in terms of a decimal number, although that is exact, right? That's a perfect thing. This will just be approximate because it's a decimal of square roots. 0.464, 7.196. Cool. All right, so at this point, we want to figure out what its length is. So the length of u plus v is going to be equal to the square root of each of its components added together and, well, squared and then added together. So its two components were 0.464 squared plus 7.196 squared. What's that wind up coming out to be? We work that out, and that winds up coming out to be, sorry, I couldn't find it in my notes, 7.211. Right, it comes out to be approximately 7.211. If we want to figure out what the angle that it's at, first thing we probably want to do is we probably want to draw a quick diagram so we can see it. So remember, it was at this one right here in terms of its components. So 0.464, just a little bit over x component, and then 7.196 up. So it's like this. So we can see that that should be what the angle is like. So remember, tan theta is equal to the side opposite divided by the side adjacent. The side opposite in this case will be the vertical height divided by the side adjacent of 0.464, the horizontal amount. We take the arctan of both sides, so the inverse tan of 7.196 over 0.464. We plug that into our calculator, look it up in a table, and that comes out to be approximately 86.31 degrees. Great. All right, next one. What is the magnitude of the vector u equals 4, 3, 12? And then we want to figure it out by both the formula we were given and the Pythagorean theorem. So first off, the formula that we've got, this is the easy part. So nice, handy formula is going to be the square root of each of its components squared, 4, 3, and 12, and all added together. We work this out, we get square root 16 plus 9 plus 144 equals, add those together, 16 plus 144 gets us 160, 160 plus 9 gets us 169, which simplifies to square root of 169 is 13. So there is the length of our vector. Now we also want to figure out through the Pythagorean theorem, right? This is where we're going to understand why this formula, why this mystical formula actually works and makes sense all the time. So first, let's see where this vector would get plotted out to. So we're going to have to look at this three-dimensionally. And while we haven't talked about three-dimensional coordinates before in this course, you've probably seen them at some point previously in some course. So here's our x, our y, and our z coordinates. So we go out 4, 3, 12, right? So 4 out on the x, a little ways out on the x, a little less way out on the y. So we're out here, right? 4, 3, 4, 3, and then we go up by 12. So our vector is like that. Now notice, we had to get out here to this place by the x and the y part first. So we can figure out what is the length here, and then we've got a square angle here as well. So let's figure out, we can break this down into two parts. The xy plane, what's happening in the xy plane. So in the xy plane, we've got 4, 3 as the cross section here, right? I'll color it so this part here is the same as this part here. So we figure that out. So that's 3 there as well. So we're going to wind up getting square root, Pythagorean theorem, square root of 3 squared plus 4 squared equals square root of 9 plus 16 equals square root 25 equals 5. Great. So we figured out what the lower part is on the bottom part. Now we can do sort of this cross section. So we can do a cross section with the z-axis included. So now we look at a cross section. So using this cross section, we can cut this and we can see, here's the thing we're trying to figure out, the length of this. And we know that the z amount was 12. So cross section with the z-axis, right? This here maps to this part here. And then here, our purple part shows up here. So that was length 5, as we just figured out. We use the Pythagorean theorem here. So once again, the value of our hypotenuse is going to be the square root of 12 squared plus 5 squared. So square root of 144 plus 25. Square root of, add those together, we get 169, which equals 13. Hey, that's the exact same thing that we saw over here when we used that formula. Cool, it works out both ways. Now let's understand, why does it work out both ways? Well, notice, The thing here for the purple line was the square root of 3 squared plus 4 squared. It was the square root of the x squared plus the y squared. The horizontal and the first component and second component put together squared. Now notice, we wind up just plugging in the purple part because it makes up one of the parts of our triangle here. So we could have alternatively looked at the square root of 12 squared plus the purple part, as that's what's going to go in there, square root of 3 squared plus 4 squared, because that's what the purple part winds up being. And then, as we're going back to using Pythagorean theorem, that whole thing's going to be squared as well. Well, hey, that means square root of 12 squared plus, if we've got square root then being squared, right, square root on top of squared, well, other way around, squared on top of square root, that cancels out. We've got plus 3 squared plus 4 squared. And hey, look, that's the exact same thing that we've got up here. And so that's where we're getting the ability to just put them all together, stack them all together, is because we have to figure out one cross-section after another cross-section. But if we then plug in the way these cross-sections wind up working out, each of the square roots that would go in from a cross-section would get canceled by the next cross-section it goes into. And so ultimately we wind up getting this form of first component squared plus second component squared plus third component squared until we get to our last component squared and adding them all and taking the square root. And that's why we've got that formula for the magnitude. All right, next up, a box weighing 300 newtons is hung up by two cables, A and B. Using the diagram, figure out how much tension is in each cable. So the first thing to do is to understand what the heck does this mean, right? A lot of math problems get thrown at us like this, where they're actually pulling from physics, and they're sort of assuming that we know stuff about physics that we might have no idea about, right? This is a math course, not a physics course. So let's first get an understanding of what the heck this means. So if we have a box on a string, just imagine, bear with me for a moment. If we have a box on a string, now imagine it weighs 100 newtons. And if you didn't know, a newton is the unit of force, and weight in the metric system. They use kilograms for mass, but force, how hard something is being pushed or pulled, that's newtons. In the English system, the British imperial system, it's pounds. So pounds is used for weight and force, although we actually have another unit for mass, but you almost never hear it. It's called slugs if you're using the British imperial system. But yeah, so newtons is a way of measuring about weight, weight is just a question of how much is gravity pulling. Okay, so imagine that this thing is being pulled down by 100 newtons of gravity, right? We've got 100 newtons of force pulling down on this thing. Well, if we've got some rope or some string that's holding this thing up, well, if it's being pulled down, it must be that the string is pulling back up. Otherwise, the thing would fall to the ground, right? So how much is the string pulling up by? Well, the string must have a tension pulling up of 100 newtons in the opposite direction. So 100 newtons going up and 100 newtons going down. Now notice, as a vector, this would be a positive 100 newtons, right? Because it's in the up direction. As a vector, this would be a negative 100 newtons in the down direction. So if we take positive 100 newtons and we add that to negative 100 newtons, we get 0. This makes sense because no force means no acceleration, right? The thing is currently stopped, so as long as it doesn't have any acceleration to make it move somewhere, it's going to not pick up any motion. So what we have to have is we have to have no force out of it for it to not move. Now, since it's hung up by two cables, it's perfectly reasonable to say, yeah, if it's hung up, it's not currently moving anywhere, it's not falling to the ground, it's not swinging left and right, it's just hanging there in space, it's sitting there. So that means that it must be a total of 0 for what is going down and what is going up. We know that it's 300 newtons going down, so now it's a question of how much is going up. So now we need to talk about these cables. So we can think about A as being a vector pulling out and away because it's pulling up on that box, right? Otherwise it'd be helping the box fall. So this is some vector A, and it has some force tension. So we'll say A is equal to the tension in A. And we'll do the same thing over here with B. So now we've got some vector B, and B will be the amount of the tension in B. So how much it's being pulled up by. Now, we want to figure out, we don't know what A and B are. That's what we're trying to figure out. But we want to figure out how to get to them. So we start looking at this and we go, well, I don't know a lot, but they did tell us this information about the angles, right? So maybe we can break these vectors up into component forms based on these angles. So we can have, if we've got 40 degrees here, then we must have 90 minus 40 here, and since this is another right angle, that means we've got 40 here again. Similarly, same basic idea, since it was 70 up here, then we've got 70 down here. So with that in mind, we can figure out what the pieces are here, right? So we know that A is the length of this hypotenuse. We don't know what the number is yet, but we're calling it A. So the vector A is going to be broken into the components. The horizontal amount is the side adjacent to 40. So A, the length of the whole thing, times side adjacent of the angle. And then A times opposite if we want to talk about the vertical part right here. So that'll be A sine 40 over here. Next, we know that we can talk about vector B. We can break it down in very much the same way. So that'll be B times cosine of 70, because its side adjacent is 70, and B times its side opposite. Sorry, not its side adjacent. Its side adjacent is not 70, but the angle connected to side adjacent is 70 degrees, and B times sine 70, right? So we can get this all just from basic trig stuff. Here's B, so we can multiply B, our hypotenuse, and figure out what the side opposite are based on this. So we've got two vectors here, A and B. One other thing that we know is the force vector. So what is the force on this box? Well, it must be that the force on this box, is it moving up and down? Is it currently still? Well, it's currently still. It's not moving anywhere. So it must have, and it's not moving anywhere horizontally, and it's not moving anywhere vertically. So total force, in the end, once everything gets put together, it's not moving up and down, it's not moving left to right, so it must be 0, 0. And they did tell us one other piece of information, 300 newtons, so the weight is equal to 0 because it's moving it's not perfectly down, so it doesn't have any horizontal, and minus 300 because it's moving down. Great. At this point, we actually have enough information to solve it. Let's work this thing out now. So remember, we've got weight equals 0, negative 300. And we know when we combine the weight with the cable, each of the cables, once we put all of these forces together, all the forces put together must come out to be a force of nothing because the box isn't moving anywhere. It's not being shoved around. So we can plug all of these things together. So we've got A plus B plus the weight vector is going to equal our total force of 0, 0. So let's work out what that is. So we've got negative A. Oh, that was one thing I didn't say on the previous slide. I put it as A cosine 40 because A cosine 40 is the length of this side, but it has to be negative because remember, when we go to the left, it is negative in the x direction, so it's negative. Both of the verticals are positive because they're both pointed up, but only the B is pointed to the right and thus pointed positively horizontally as well. All right, so we've got negative A cosine 40, A sine 40, plus B cosine 70, comma, B sine 70. Sorry, I'm going to have to continue on to the next line. Remember, this is just all one line put together. So plus 0, negative 300. In the end, we'll wind up equaling 0, 0. So let's combine this all together. We'll switch to the color of green for everything together. So we've got negative A cosine 40 plus B cosine 70 plus the 0 from the weight. That comes out to be the total for our first components, and then A sine 40 plus B sine 70 minus 300 equals 0, 0. So at this point, we know the component must equal the first component on the left side of equation has to be the same as the first component on the right side of the equation. Same thing, second component on left side must be the same thing as second component on the right side. So we can break this down into two separate equations. So we've got negative A cosine 40 plus B cosine 70 equals 0. So we can get B on its lonesome, or A on its lonesome, and then plug that into the other one. So let's solve for that first. B cosine 70 equals A cosine 40. So at this point we see that B is equal to A times cosine 40 over cosine 70. We can plug that into a calculator right now and get some number out of it, but then we have to write all these decimals, so we can just leave it like that for now. Next, we'll swap to a new color for solving out this part. So we've got A sine 40 plus B sine 70 minus 300 equals what was on the right-hand side, 0. So we can move the 300 over. We see we've got a sine 40 plus b sine 70 equals 300. Now, we see that b is the same thing as a times cosine 40 divided by cosine 70. So we've got a sine 40 plus, we swap out our b, a times cosine 40 over cosine 70 times sine 70 still equals 300. So at this point, we pull out all of our a's. We've got a times sine 40 plus cosine 40 over cosine 70 times sine 70 equals 300. Notice that there's nothing we can cancel out there because we don't have any exactly matching things, but we can divide by it. 300 divided by sine 40 plus cosine 40 over cosine 70 times sine 70. We can plug that all into a calculator, and it will come up and give us an answer, and it will tell us that A is approximately equal to 36.40. Oh, whoops, sorry, not 36.40, but times 3. Give me just a second. The magic of video, right? So it comes out to be approximately 109.2. And that's our value for A. To figure out our value for B, we've got this handy thing right here. So B equals A, which was 109.2, times cosine 40 divided by cosine 70. We work that out with our calculator, and we get approximately 244.6. So B, the tension in B is 244.6 newtons, and the tension in A is 109.2 newtons. Great. Those are our solutions. All right. Last example, a plane has a compass heading of 75 degrees east of due north and an airspeed of 140 miles per hour. If the wind is blowing at 20 miles per hour and towards 10 degrees west of due north, what is the plane's direction and speed relative to the ground? So first, what's this first part mean? We've got compass heading 75 degrees east going at 140 miles per hour airspeed. So airspeed means your speed in the air, how fast you're moving relative to the air right around you. So if that's the case, then our plane is moving 75 degrees east of due north. So due north is this way, right? Our vertical axis. So if that's the case, we need to curve 75 degrees down towards the east. So east is this way, so that's 75 degrees here. So if we want to figure out what's the thing in here, because we'll probably want that for figuring out other things, that's going to be 15 degrees, right? So it's 15 degrees for our normal theta that we're used to. Okay, so that's the plane, the direction that the plane is headed is going like that, right? It's going off in this way. But then, that's its airspeed. The air also is able to move. So the air is going this way. The air is blowing the plane. So the plane's going like this, but at the same time it's being blown off course slightly by the wind. Or perhaps, hopefully, they've taken this into account and it's not going off course. So we've got the wind blowing at 20 miles per hour and towards 10 degrees west of due north. So once again, it's off of due north, and now it's just a little off 10 degrees off here, and it's a total of 20 miles per hour. So we've got 140 miles per hour this way and 20 miles per hour, 10 degrees to the west of due north. So notice that the total angle for that is going to wind up being 100 degrees if we wanted to figure that out, or we could also look at it in terms of 80 degrees here as well. So depends on which one you think is easier. I'm going to go with the one inside of the triangle, and we'll just have to remember to deal with the fact that our horizontal is going to be negative when we're working on the wind. So the plane, what is the velocity of the plane in the air? Right? To be able to figure out what the plane's direction and speed is relative to the ground, we have to combine its motion in the medium with the medium's motion relative to the ground. Right? Its motion in the medium is the 75 degrees east of due north, and an airspeed of 440 miles per hour. The blue part, and the red part, the wind blowing, is the wind relative, the air relative to the ground. So we have to combine those two things. So the velocity of the plane in the air, its horizontal component is going to be the length of the vector, 140, times the angle we've got is 15. So if we're talking about the horizontal, that's going to be side adjacent. So cosine 15, 140 times sine 15 for the vertical, because that's side opposite. We work that out, and that winds up coming out to be approximately 135.2 and 36.23. And the units on both of those are miles per hour, because it's moving 135.2 miles per hour north and 36.23 miles east simultaneously. And then we've got the wind. What is the velocity of the air itself? So the air is moving at a speed of 20. And if we want to figure out its horizontal component, it's going to be this part here, at which point we go, oh, right, it's going negative, so let's put in that negative sign, as it's moving to the left. You have to remember to catch those negatives. Pay attention to, is it going to be a positive or negative direction for everything? So that's going to be 20, the size of it, times cosine of 80 degrees in this case, and then positive 20, because this one's going positively, times sine of 80. Work that one out with a calculator, and we get 131.7, 55.93. Oh, whoops, sorry. I wrote the entirely wrong thing. I meant to write negative 3.47. Read the wrong thing off of my notes. Negative 3.47, comma, 19.70. Great. All right, so if we want to figure out the combination of the two, if we want to figure out what is the total motion of the plane relative to the ground, so the total motion, that's going to be the plane's motion relative to the air plus the air's motion relative to the ground. We just figured out what each one of those is, so 135.2, comma 36.23 was our plane's motion, plus negative 3.47, comma 19.70. And so in total, that gets us 131.7, 55.93. Great. So that's what our velocity for the velocity vector is going to be, what the component form is. However, it asked for speed and direction of the whole thing put together. So if that's the case, we want to figure out speed. Well, speed is just the size of our velocity vector. So size of our velocity total vector. So that's going to be the square root of the first component of our total vector, 131.7 squared, plus the second component squared, 55.93 squared. We take the square root of that, figure it all out using our calculator, and we wind up getting 143.1 miles per hour. So the plane is actually going a little bit faster than its speed had been previously without the air connected to it. However, its direction will also change. To help us figure out direction, let's draw just a quick picture so we know what's going on. So we've got this right here as our motion. So 131.7, fairly horizontal, and a little bit, between a third and a half of our amount horizontal up. So that's sort of what our motion is like total. So none of my picture is totally not relative. The 140 up here should be much longer than the 20 here, and this 143.1 mile per hour long vector should be even longer, but that's okay. We're just trying to get a sense of what's going on. They're sketches, not perfect drawings. So we're looking for this angle here. So tan of theta is going to be the side opposite, the vertical component, 55.93. divided by side adjacent, the horizontal component, 31.7. We take the arctan of that. That gets us theta equals about 23 degrees. Now notice, that's what theta is equal to. Theta equals 23 degrees. All of the stuff was given in east of due north. So we have to put it in that same thing. So if it's 23 degrees as our theta here, that means it's 23 degrees going up from our positive x-axis, which was east. So up would be towards the north. So we could phrase this as 23 degrees north of east. Alternatively, if we wanted to use the exact same thing that they had done when they all talked about east of due north, 90 minus 23, if we want to figure out what this is here, 90 minus 23 equals 67. So we could also talk about it as 67 degrees east of north. East of north. Either one would be fine, but we have to put it in the same format because theta, they didn't give us a theta previously. We don't know where theta is based off of, so we have to make sure we're following the same pattern of east of due north, west of south, something like that. We have to go in that same pattern. All right, vectors are really, really useful. We'll talk about them more. We'll talk about how matrices are connected to them, but really great stuff here. We've talked about a whole lot of things here, so just, if you had any difficulty understanding this lesson, just try watching piece by piece and just work examples one after another. There's a lot of things to digest here, but they all work together, and vectors are so useful. All right, we'll see you at Educator.com later. Bye.